So the last theorem that we have in section 4.5 is related to the first derivative test, but it's called the second derivative test. Right? Not surprisingly, this test is going to use the, what do you think? The second derivative of a function, all right? So, and it is also to help you find these local extrema. So let me go ahead and write this down. Again, I'm going to sort of skip the technical hypotheses like the second derivative being continuous over an interval containing C and all that. So here's an informal version of this. Suppose you find a critical point. Suppose you find that the first derivative at C is equal to 0. All right, so C is a critical point of the function. Now, here's the thing. If, and by the way, you know, it could be maximum, it could be minimum, or it doesn't have to be either, right? So when you have, oops, that's too much. When you have a cubic function, for instance, the derivative becomes 0 at the origin, but it's not a maximum or minimum. All right, so if you find a place where the derivative of a function is 0, and if the second derivative is positive, what does it mean? Well, it means that it's concave up. This part is concave down. This part is concave up. So if you have a horizontal tangent, and if the derivative is second derivative is positive, meaning it's concave up, then f has a local minimum at C. So the graph goes like this. Okay, right here. It looks like a smiling face. Yeah, happy. All right. And then second, if f double prime is negative, okay, so that means concavity is down, that we're talking about something like this, then f has a local maximum at C. Graph looks like this. Here's a point. All right. And so this is the maximum point. Concavity is down. You may, many people think, you know what, this sounds weird, because if you think, you know, if the second derivative is positive, if anything is positive, it seems like you should have a maximum. But no, it's the other way around. Okay. The second derivative positive means concavity is up, and so you have a local minimum. And if the second derivative is negative, that means the concavity is down and you have a local maximum. See, when you're at the maximum point, the only direction you can go is down. That sounds so depressing. When you're at the highest point in the world, like you're at the top of the world, the only direction you can go is down. So that may be a way to remember, a depressive way to remember, but just keep this in mind. This is the second derivative test. Oh, what happens then if the second derivative is 0? Okay, so it'll be a case like this, where the second derivative is of x cubed is, it's going to be 0, right? 3x squared, and then you have 6x. The derivative is 0 at this point. Then the test fails. The test fails means you cannot draw any conclusions. You can say the test is inconclusive. That's another way of saying that. Okay, so that's called the second derivative test. I want to emphasize one very important thing here. Both the first and second derivative test is to find what? Local relative extrema. Okay, not absolute extrema. Do you remember how you find your absolute maxima and minima? You find the critical points and endpoints and evaluate the functions at all of these usual suspects, right? Quote unquote usual suspect points, which are the endpoints and the critical points. You do not have to use second or first derivative test if you're looking for absolute extrema. This is very common. It's a common mistake for first semester calculus students. Right? You do not use first or second derivative tests if you are looking for absolute extrema, because these tests are going to give you local arguments, okay? Not the absolute maximum or absolute minimum. All right, so with that in mind, let's do this first example. Very simple function, y is equal to x squared, right? You know there is one relative or local minimum and no local maximum to this function. Well, let's verify that f prime x is 2x, which is 0. If x is equal to 0, that's the only critical point. The second derivative at this point is 2. And in fact, the second derivative is 2 everywhere. That means concavity is up everywhere, which you already knew because this is a concave up parabola. And so that's greater than 0. And therefore, what can you conclude? F has a, according to the first part of the second derivative test, F has a local minimum at x is equal to 0 because the concavity up is up at that critical point. All right, I'm going to do one more problem, which is in the book. It's called example 4.20 in the OpenStax volume 1 book of calculus. And so that problem has to do with this polynomial function. F of x is x to the 5th minus 5 times x to the 3rd power. All right, and the question says, well, I'm going to pose the question. Find all local extrema. You better find all of them. And then try to sketch the graph of this function. Now, when you encounter a new problem like this, my suggestion is, if time allows, and hopefully it does, sit back and just start to come up with your strategy, or maybe just start a conversation. Get together with your math friends and put this on your card and put it on the table and say, hey, feel free to talk about this function. Do you like it? Is this one of your favorites? What do you know about this one? Tell me everything you know about this function. And somebody will say, well, it's a polynomial function. That means it's a nice function. It's continuous everywhere. The domain is all of the real numbers, the set of all reals, and it's continuous everywhere, differential everywhere. Therefore, it's nice, no gaps, no asymptotes. You can keep talking and talking. The fact that it's a 5th degree polynomial and the leading coefficient 1 is positive means that you have, whatever happens here, close to the origin, lots of things, ups and downs could happen. And in fact, because it's a 5th degree polynomial, there could only be, 4 ups and downs, 4 local maxima and minima, because the first derivative is going to be a 4th degree polynomial. You can say a lot of things, but the end behavior is going to be like this. Did you know that? As x approaches infinity, f of x approaches infinity. As x approaches negative infinity, the f of x approaches negative infinity. This is a characteristic of a odd degree polynomial, all that stuff, right? Okay, now you are becoming a little familiar with your new friend f, which is a 5th degree polynomial. Let's get to know this polynomial a little better. You spend more time, that's how you get to know people and functions. All right, so f prime is 5x to the 4th minus 15x squared. All right, you can factor 5x squared and you get x squared minus 3, right? Now, to find the local extrema and to apply the second derivative test, you have to find critical points. So you set this equal to 0. You know that the derivative exists at every point because it's a polynomial. So you don't have to worry about the derivative being undefined or whatever. Okay, so this is a 4th degree polynomial. Oops. You have x times 5, and then x plus root 3, x minus root 3. You don't actually have to factor this, but this makes it easier for you to see that there are, these roots of this 4th degree polynomial, right? That's 0, 0. That 0 is a repeated root with the multiplicity of 2 because you have x squared in here, and that's x minus 0 to the squared. And then you have plus or minus square root of 3. Okay, so those are the places where the derivative is equal to 0. In fact, we found exactly 3 critical points and no more. Okay, now you can apply the first derivative test at this point, and that means you will make a little chart, like this. sign chart, and then you can figure out when this derivative is plus or minus. Okay, so that's okay too. And in fact, you may want to do that. I may want to show you how to do that. But to apply the second derivative test, now you found your critical points, okay? And we are going to check if the second derivative is positive or 0 or negative at each of these points. And to do that, of course, you have to find the second derivative, which is 20x to the fourth, 20x cubed minus 30x. You can even factor 10x out of each term. So you have 2x squared minus 3, right? And you can't really, well, I mean, you can factor this, but you don't have to, right? Let's try to figure out what happens at 0. Well, that's 0. Ooh, the test fails here. Can't do much with this. How about at square root of 3? All right, so this will be 10 square root of 3 times 2 times, what's square root of 3 squared? Well, square root of 3 squared by definition is 3, right? So that's 3. All right, so this is, inside of that is 6 minus 3. So that's 30 square root of 3. That's positive. What happens if you plug in negative square root of 3? Well, that's 10 times negative square root of 3 times 6 again, because this part is independent of whether the radical is positive or negative, because you have squared. So it's 6 minus 3, sorry, that's 3. So that's negative 30 square root of 3, which is a negative number. So this tells me f has a local what? Minimum at square root of 3 and a local maximum. Now this is a local maximum because the derivative at negative square root of 3 is 0, and the second derivative is negative, meaning it's concave down, and this is the picture, concave down, meaning that you have a picture like this. All right, so it has a local maximum at negative square root of 3. Okay, so we have a nice picture of what's going to happen with this. Maybe not yet, okay, but we know that you have a, let's see, what did I say? This square root of 3 is a local minimum, and then you have a local maximum here, right? So the graph is going to be looking something like this at these points. We don't know what happens at this point yet. Okay, so that's a beginning. At least we know. Okay, in fact, we know that these two are the well, okay, I was going to say these are the only local maxima and minima, but I forgot there is a one point where the test failed. So let's examine a little further, right? So the second derivative test gave us all of this information. All of this information was from the second derivative test, okay? Let's apply the first derivative test and see if we can get a little more insight, okay? The first derivative test, of course, is to examine the first derivative, as the name suggests. Remember, f prime of x was this. That's 10x to, no, I'm sorry. Yeah, that's the second derivative. I need to plug in the first derivative, which is that. Okay, so that's 5x squared, x plus root 3, x minus root 3. All right, so I have this chart. Remember, this is equal to 0 at x is 0, 0 repeated, plus and minus root 3. So I have 0, negative radical 3, positive radical 3. Now 5x squared, what kind of a beast is 5x squared? Well, that's almost always positive, right? Even if the number is negative, when you square this and multiply that by 5, you get a positive. The only time this becomes 0 is when x is equal to 0. So, and this interval, it's positive. In this interval, it's positive. right at this point, 5 times square root of 3 squared is, of course, 15. That's positive. It's almost positive everywhere except at 0. Oh, all right. Then let's look at the second factor, which is x plus square root of 3. That's negative here, but when x is negative square root of 3, that becomes 0. And after that, henceforth, it's always going to be positive. X minus radical 3 is negative here, still negative, still negative, still negative, still negative. When x is square root of 3, finally it achieves 0, and after that it becomes positive. The derivative of the function f is the product of all of these 3. So now positive, negative, negative, that's positive. Wait, is that right? Of course it's right. 2 negatives multiplied together is going to give you a positive number, right? 2 wrongs don't make it right, but 2 negatives make it positive. This is 0, positive, positive, negative, that's negative. 0, positive, positive, negative. Oh, that's negative. And then you have 0 and positive. So remember my visualization based on this sign chart of the derivative. I really think that's a great idea for you to practice. So this is increasing here. The function f is increasing here, 0 here, decreasing here, and decreasing again. All right. This was the question we didn't know. The second derivative test failed when x was equal to 0. And it looks like maybe it wasn't a maximum or minimum. It just keeps going down. Okay. But with this, you have a lot of information now. Okay. And in fact, let's go ahead and try to sketch this graph with all the information that we have so far. Now, in order to draw this accurately, you may need to have a little more information, but at least we know something. We know a lot of things about this function now. For instance, when x is square root of negative 3, 0, and square root of 3, these are important points. Okay, and in fact, what is f0? Where's my function? Yeah, this is the function, right? So f of 0 is clearly 0. Oh, by the way, f is also odd. I don't mean f is a strange, weird personality. You know, f is like somebody's odd. No, when I say a function is odd, that means f of negative x is negative f of x, which means the right-hand side is going to be exactly the opposite of the left-hand side. So if you know the one side of the function, you know the other side. X cubed minus 5x squared. So f0 is 0, which means it goes through the origin, all right? And we are also told that it's what is that? Before negative square root of 3, it's positive. Sorry, the derivative is positive. And you have a local maximum, and then it starts to go down, and it continues to go down. And at this point, it starts to go up, right? Because you have a local maximum here and local maximum here and local minimum here. By the way, this is just my sketch, and this is not part of the graph, right? So that much we already know. And what else do we know? We do know, well, so this is kind of hard. We didn't do a sign chart for concavity, all right? But what we do know is that the derivative is 0 right at this point, right? So you have a horizontal tangent line here. And that happens to be at the origin, okay? And so my guess is that it's going to, here's a horizontal tangent, and it starts to go down, okay? And down, down, down. And at this point, it starts to go up again, right? And so it's going to go up this way. And the other side is exactly the opposite of this. So you're going to keep going up. And you have a local maximum here. So then it starts to go down this way. All right. So this point is symmetric to this point. And, one is a local minimum. And the other is a local maximum. I don't know how big the value is here or how small the value is here. That you would have to plug in. Okay. In fact, we could do that. actually. It's going to be complicated because we don't know these numbers. What is this? That's 3 to the 5 halves minus 5 times 3x, x is 3 to the 3 halves. Okay, unless you have a calculator, you really can't figure out these numbers. Okay, but that's this point here. The y value of this point happens to be this, and the negative of that, opposite of that, is going to be a positive number, which is the y value at this local maximum. While we don't know these things, we do know the rough sketch of this graph, which will look like this, okay, based on our first and second derivative analyses. At least we know that there is a local minimum at square root of 3 that's coming from the second derivative test, and there's a local maximum at negative square root of 3, again, based on the second derivative test. And if you want to sketch this more accurately, of course, you can plug in some numbers and plot some points and do all that. But again, you see how the fact that this is an odd function sort of helped us out, because just drawing one side, the other side is going to be very similar. All right, so that concludes our section 4.5. And so do your homework and get to know how you apply first and the second derivative tests.